Hello there, and welcome to the Sleepy Library. Tonight, we are entering one of the most mysterious realms of human experience, where consciousness fades and the mind creates entire worlds from nothing. We will journey through the science of sleep and dreams, exploring what happens in your brain during those precious hours when you surrender to rest. This is a place where neurons dance in synchrony, where memories are woven into lasting knowledge, and where the brain cleanses itself of the day's accumulated burdens. If you find comfort in these quiet explorations of science, consider subscribing. It helps others discover this peaceful corner of knowledge, one restful soul at a time. But for now, let your shoulders drop. Let your breathing become slow and even. You have nowhere to be but here, settling into the gentle mysteries of the sleeping brain. Let's begin. Your brain never truly sleeps. Even when you lose consciousness and the world fades away, your brain remains remarkably active, engaged in processes that are essential to life itself. The sleeping brain is not resting in the way we might imagine. Instead, it is working, reorganizing, repairing, and preparing you for the challenges of tomorrow. Scientists have spent over a century studying sleep, and what they have discovered challenges our basic assumptions about what it means to be unconscious. Sleep is not a single state, but a complex journey through different stages, each with its own signature patterns of brain activity. Throughout the night, your brain cycles through these stages in a rhythm that repeats approximately every 90 minutes, each cycle bringing different gifts to your mind and body. The architecture of sleep is both elegant and intricate. When you first close your eyes and begin to relax, your brain starts to change its electrical patterns. The fast beta waves that characterize alert wakefulness begin to slow into the gentler alpha waves of drowsiness. Your heart rate decreases. Your breathing becomes more regular. Your muscles start to relax, sometimes with small twitches, as motor neurons fire their final bursts before quieting. This is the threshold between waking and sleeping, a boundary that is surprisingly fluid and complex. Scientists call this stage 1 of non-rapid eye movement sleep, or NREM sleep. It typically lasts only a few minutes, a brief transition during which you can be easily awakened. Your brain produces theta waves during this stage, slower oscillations that signal the beginning of your journey into deeper unconsciousness. From stage 1, you descend into stage 2 NREM sleep, a period of light sleep that makes up the largest portion of your total sleep time. This stage is marked by distinctive features in your brain's electrical activity. Sleep spindles appear, brief bursts of rapid brain waves that last only a second or two. These spindles, which occur about a dozen times per minute, are thought to play a crucial role in memory consolidation. They may act as a protective mechanism, helping to shield your sleep from external disturbances. During stage 2, your body temperature drops further and your eye movements stop. K-complexes also emerge, large waves of brain activity that may help suppress cortical arousal and keep you asleep. These complexes might also play a role in memory consolidation, helping to move information from temporary storage into more permanent neural networks. Then comes the descent into stage 3, also known as slow-wave sleep or deep sleep. This is the most restorative stage of sleep, the time when your brain produces its slowest, highest amplitude waves, called delta waves. During deep sleep, it becomes much harder to wake you. If someone does manage to rouse you from this stage, you will likely feel groggy and disoriented, a state scientists call sleep inertia. Your blood pressure drops during deep sleep. Your breathing becomes slower and more rhythmic. Your muscles are relaxed, but not paralyzed. This is when your body performs much of its physical restoration, releasing growth hormones that repair tissues and build bone and muscle. For your brain, deep sleep is a time of remarkable activity beneath the surface of consciousness. This is when the glymphatic system, your brain's waste clearance mechanism, operates at peak efficiency. After progressing through these NREM stages, your brain begins to change again, emerging into a radically different state called rapid eye movement sleep, or REM sleep. During REM, your brain becomes almost as active as it is when you are awake. In fact, if you were to look at an electroencephalogram recording of REM sleep, the brain waves would be nearly indistinguishable from those of waking consciousness. Your eyes move rapidly beneath your closed eyelids, darting back and forth as if you were watching some invisible scene unfold. Your heart rate increases and becomes more variable. Your breathing quickens and becomes irregular. Yet, despite this brain arousal, your body enters a state of temporary paralysis. The brainstem sends signals that prevent your muscles from acting out the mental experiences occurring in your sleeping brain. This paralysis is essential, a safety mechanism that keeps you from physically responding to dreams. REM sleep is when most of your vivid, narrative dreams occur. The dreams of REM sleep tend to be bizarre, emotional, and hallucinatory, filled with impossible events and strange juxtapositions that your sleeping mind accepts without question. During REM, certain brain regions become highly active, while others quiet down. The visual cortex lights up with activity, creating the rich imagery of dreams. The amygdala, a structure involved in processing emotions, becomes increasingly active, which may explain why dreams often carry such emotional weight. The hippocampus, crucial for memory, shows patterns of activity that suggest it is replaying and consolidating experiences from your waking hours. Meanwhile, prefrontal cortex, the brain's center for logical reasoning and self-awareness, decreases its activity. This may be why dreams often lack logical coherence, why you rarely question the impossible events unfolding in your sleeping mind. Throughout a typical night, you cycle through these stages 4 or 5 times. Early in the night, you spend more time in deep NREM sleep, with shorter periods of REM. As the night progresses, the cycles shift. Deep sleep becomes briefer, while REM periods grow longer. By morning, you may spend 30 minutes or more in a single REM period, experiencing extended sequences of dreams. This changing pattern suggests that different stages of sleep serve different purposes. The deep sleep of early night may focus more on physical restoration and clearing waste from the brain, while the extended REM periods of late night may emphasize memory processing and emotional regulation. The discovery of REM sleep in 1953 revolutionized our understanding of what happens during sleep. Before this, most researchers believed that sleep was a passive state, a simple turning off of consciousness. But when Eugene Azarinsky and Nathaniel Kleitman at the University of Chicago observed rapid eye movements occurring regularly during sleep, they realized that something active and purposeful was happening. When they woke people during these REM periods, the subjects reported vivid dreams about 80% of the time. When awakened from non-REM sleep, people reported dreams much less frequently, and the dreams they did recall tended to be more thought-like and less vivid. This discovery established that dreaming was not a random occurrence, but was linked to specific, recurring stages of brain activity. Since then, neuroscientists have mapped the brain regions and neural circuits involved in generating and regulating sleep. Deep in your brain, a small region called the hypothalamus contains groups of nerve cells that act as sleep control centers. Some of these cells promote wakefulness, while others promote sleep. The balance between these competing systems determines whether you are awake or asleep. The suprachiasmatic nucleus, located in the hypothalamus, serves as your brain's master clock, synchronizing your sleep-wake cycle with the external cycle of day and night. This tiny cluster of cells receives information about light exposure directly from your eyes and uses this information to regulate the production of melatonin, a hormone that promotes sleep. The brainstem, located at the base of your brain, plays a special role in controlling the transitions between wake and sleep and between different sleep stages. During REM sleep, the brainstem sends signals that both activate the cortex, creating dream experiences, and paralyze the body, preventing dream enactment. The pons and medulla, structures within the brainstem, are essential for generating the characteristic features of REM sleep. The thalamus acts as a relay station for sensory information. During most stages of sleep, the thalamus becomes quiet, allowing you to tune out the external world. But during REM sleep, the thalamus becomes active again, sending the cortex images, sounds, and other sensations that fill your dreams. The basal forebrain, located near the front and bottom of the brain, promotes both sleep and wakefulness through different neuron populations. The midbrain contains a system that helps keep you alert during the day. Throughout your brain, the release and suppression of various neurotransmitters regulate these transitions. Adenosine, a chemical that builds up in your brain during waking hours, makes you feel increasingly sleepy as the day progresses. Caffeine works by blocking adenosine receptors, temporarily preventing you from feeling tired. GABA, another neurotransmitter, reduces neural activity and promotes sleep. During REM sleep, the release of acetylcholine increases, while norepinephrine and serotonin are suppressed. These changing chemical environments create the distinct characteristics of each sleep stage. The regulation of sleep involves two fundamental processes working together. The first is your circadian rhythm, an internal biological clock that operates on a roughly 24-hour cycle. This rhythm is generated by genes within nearly every cell in your body, but it is coordinated by the suprachiasmatic nucleus in the hypothalamus. Your circadian rhythm influences not just sleep and wakefulness, but also body temperature, hormone release, and countless other physiological functions. The rhythm responds primarily to light, which is why bright light exposure in the evening can delay sleep, while bright light in the morning can help you wake up and feel alert. The second process is sleep drive, also called sleep pressure. The longer you stay awake, the stronger your need for sleep becomes. This is partly mediated by the accumulation of adenosine in the brain. Unlike circadian rhythm, which cycles independently of whether you are awake or asleep, sleep drive builds continuously during wakefulness and dissipates during sleep. These two systems can sometimes work at cross purposes. Have you ever felt exhausted in the late afternoon, but then experienced a second wind in the evening? This happens because your circadian system promotes wakefulness in the evening hours, even as your sleep drive continues to build. The interaction between these systems helps explain why shift workers often struggle with sleep. Their circadian rhythms remain tuned to the day-night cycle, even as they try to sleep during the day and stay awake at night, creating a persistent mismatch between their biological rhythms and their schedules. One of the most fascinating discoveries in sleep science is that sleep is not uniform across the brain at any given moment. Even when you are clearly asleep by behavioral criteria, some parts of your brain may say activity patterns more similar to waking, while other parts show deep sleep patterns. This local aspect of sleep helps explain some puzzling phenomena. It may explain why you can sleepwalk, with motor areas of your brain active enough to generate coordinated movement while most of your brain remains asleep. It may explain sleep talking, where speech areas become briefly active during sleep. It might even help explain that peculiar state many people experience when falling asleep, where you remain aware of your surroundings yet cannot move, a condition called sleep paralysis. Recent research has revealed that the boundary between sleeping and waking is much less sharp than we once believed. As you fall asleep, different parts of your brain do not shut down all at once. Instead, they gradually transition at different rates, creating a mosaic of neural states. Some brain regions may be deeply asleep, while others are still relatively active. This mixing of sleep and wake states in different brain regions may be most prominent during the transition into sleep and during sleep deprivation. When you are severely sleep deprived, local regions of your brain may briefly enter sleep-like states, even while you are behaviorally awake, leading to momentary lapses in attention and performance. The glymphatic system represents one of the most important recent discoveries in neuroscience. For decades, scientists puzzled over how the brain cleared away metabolic waste products. Unlike other organs, the brain lacks a conventional lymphatic system for waste removal. In 2012, researchers discovered a previously unknown network of channels that clears waste from the brain during sleep. They named it the glymphatic system, combining glial, referring to the support cells of the brain, and lymphatic. This system uses cerebrospinal fluid, the clear liquid that surrounds the brain and spinal cord, to flush away waste products. Here is how it works. Cerebrospinal fluid flows into the brain along the outer walls of arteries, moving through spaces called perivascular channels. This fluid then moves into the interstitial space, the microscopic gaps between brain cells, where it mixes with the fluid surrounding neurons. As the cerebrospinal fluid flows through these spaces, it collects metabolic waste products, including proteins like amyloid beta and tau that have been linked to Alzheimer's disease. The fluid then carries these wastes away along the outer walls of veins, eventually draining into the lymphatic vessels in the neck. What makes this system remarkable is that it operates primarily during sleep. During waking hours, the interstitial space between brain cells is relatively narrow, and the flow of cerebrospinal fluid is limited. But during sleep, particularly during deep slow-wave sleep, the interstitial space expands by about 60%. This expansion dramatically increases the flow of cerebrospinal fluid through the brain, enhancing waste clearance. The mechanism behind this expansion is thought to involve changes in the activity of norepinephrine, a neurotransmitter that is high during wakefulness and low during sleep. When norepinephrine levels drop during sleep, brain cells can relax and shrink slightly, opening up more space for fluid flow. The glymphatic system depends critically on aquaporin-4 water channels, specialized proteins that are densely packed on the end feet of astrocytes, the star-shaped support cells that wrap around blood vessels in the brain. These channels facilitate the rapid movement of water and dissolved substances between cerebrospinal fluid and interstitial fluid. In mice genetically engineered to lack aquaporin-4, glymphatic clearance is reduced by about 70%. Studies have shown that as we age, the expression and polarization of these channels decreases, which may partly explain why waste clearance declines with age, and why older adults are at higher risk for neurodegenerative diseases. Recent research has begun to map the glymphatic system in living humans using advanced imaging techniques. These studies have confirmed that the system exists in people and that its function varies with sleep and wakefulness. One groundbreaking study in 2024 used contrast imaging in neurosurgery patients to directly visualize fluid flowing along defined pathways in the human brain, providing the first definitive proof of the glymphatic network in humans. This discovery has profound implications for understanding brain health and disease. If the glymphatic system is indeed responsible for clearing proteins associated with Alzheimer's disease, then anything that impairs this system, such as chronic sleep deprivation, certain sleeping positions, or age-related changes, might increase the risk of neurodegeneration. The connection between sleep and the glymphatic system may help explain why sleep is so universal across the animal kingdom. Nearly every animal that has been studied shows some form of sleep or sleep-like behavior, from jellyfish to elephants. The universality of sleep and the severe consequences of sleep deprivation have long puzzled scientists. Why would evolution favor a behavior that leaves animals vulnerable to predators? The glymphatic hypothesis offers a compelling answer. Sleep may be the price the brain pays for consciousness. During waking hours, the metabolic activity of neurons produces waste products. These wastes must be cleared, but the brain cannot clear them efficiently while neurons are actively processing information. Sleep provides the brain with dedicated time for waste removal, a kind of biological housekeeping that cannot be adequately performed while we are awake. This hypothesis is supported by studies showing that even one night of sleep deprivation can lead to the accumulation of amyloid beta in the human brain. Chronic sleep deprivation has been linked to increased risk of Alzheimer's disease, and people with sleep disorders show evidence of reduced glymphatic function. Conversely, interventions that improve sleep quality may enhance glymphatic clearance. Some research suggests that sleeping position matters, with side sleeping potentially allowing more efficient waste clearance than back or stomach sleeping, though more research is needed to confirm this. The waste clearance function of sleep has led researchers to investigate whether we can enhance this process therapeutically. Could we develop treatments that boost glymphatic function and thereby reduce the risk of neurodegenerative disease? Some studies are exploring whether enhancing slow-wave sleep through techniques like auditory stimulation or transcranial electrical stimulation might increase waste clearance. Others are investigating whether exercise, which appears to improve glymphatic function, might provide neuroprotective benefits partly through this mechanism. As we learn more about the glymphatic system, we may discover new ways to support brain health across the lifespan. Memory consolidation during sleep represents another crucial function that has been extensively documented. When you learn something new during the day, the initial memory trace is fragile and easily disrupted. Sleep helps to stabilize these memories, transforming them into more permanent forms that are resistant to interference. This process, called memory consolidation, involves multiple stages and mechanisms that unfold during different sleep stages. Both slow-wave sleep and REM sleep contribute to consolidation, though they may process different types of memories or different aspects of the same memories. During slow-wave sleep, the brain replays experiences from the day. This replay has been directly observed in animal studies, where researchers recorded from multiple neurons simultaneously. When rats explored a maze while awake, specific patterns of neural activity corresponded to specific locations in the maze. Later, during slow-wave sleep, those same patterns repeated, but on a faster timescale. The rats' brains were essentially rehearsing the maze experience. This replay is thought to help transfer memories from the hippocampus, where they are initially encoded, to the neocortex, where they can be stored more permanently and integrated with existing knowledge. In humans, brain imaging studies have provided evidence of similar reactivation during sleep. Regions that were active during learning become active again during subsequent sleep, and the degree of reactivation predicts how well the memories will be retained. In one elegant study, participants learned the locations of objects on a screen, with each object associated with a specific sound. During subsequent slow-wave sleep, some of the sounds were quietly replayed. When participants were tested later, they showed better memory for the objects whose associated sounds had been replayed during sleep, demonstrating that reactivating specific memories during sleep can strengthen them. The replay of memories during sleep does not simply strengthen them, it also appears to reorganize and transform them. Memories can be extracted from their original context and integrated with related knowledge, allowing for the formation of new insights and connections. This transformative process may be why sleep has been linked to creativity and problem-solving. Many famous discoveries and creative breakthroughs have reportedly occurred after a period of sleep. Otto Loewi dreamed the experiment that would prove chemical neurotransmission. Dmitri Mendeleev claimed to have dreamed the periodic table. While such anecdotes cannot be taken as scientific proof, controlled studies have shown that sleep can indeed facilitate insight. Participants who slept after being exposed to a hidden rule in a problem-solving task were more likely to discover the rule than those who remained awake. The mechanisms underlying memory consolidation during sleep involve the coordinated activity of multiple brain regions and the orchestration of several types of brain oscillations. During slow-wave sleep, the cortex generates slow oscillations, large waves with a frequency of less than 1 cycle per second. These slow oscillations appear to coordinate two faster rhythms: sleep spindles generated by the thalamus and sharp wave ripples generated by the hippocampus. The timing of these three rhythms relative to each other appears to be crucial for effective memory consolidation. Sharp wave ripples in the hippocampus replay memory traces. These ripples occur during the upstate of the slow oscillation, when cortical neurons are more excitable. Thalamic spindles follow shortly after, potentially mediating the transfer of information from hippocampus to cortex. Research has shown that boosting slow oscillations during sleep through techniques like transcranial stimulation or presenting rhythmic sounds can enhance memory consolidation. Similarly, disrupting spindles or ripples impairs memory formation. These findings suggest that the electrical rhythms of sleep are not merely epiphenomena, but play an active role in memory processing. The brain's oscillations during sleep create a privileged state for memory consolidation, one that cannot be easily replicated during wakefulness. During waking, the brain must process incoming sensory information and generate behavior. These demands appear to interfere with the consolidation processes. Sleep provides a period relatively free from sensory input and behavioral demands, allowing the brain to focus on internal information processing. Not all memories benefit equally from sleep. Procedural memories, which involve learning skills and habits, appear to be particularly dependent on sleep for consolidation. Studies of motor skill learning have repeatedly shown that performance improves after sleep, even without additional practice. This improvement is not simply due to recovery from fatigue, as equivalent periods of waking rest do not produce the same gains. The specific stages of sleep that contribute to procedural memory consolidation may depend on the type of skill. Some studies suggest that REM sleep is particularly important for the consolidation of complex motor skills. Declarative memories, which involve facts and events, also benefit from sleep, though the relationship may be more complex. Sleep appears to help not just with retention of declarative memories, but also with their integration and reorganization. During sleep, memories can be abstracted, with the brain extracting general patterns and rules from specific experiences. This process may be particularly important for the development of semantic knowledge and conceptual understanding. Sleep may also play a role in emotional memory processing, helping to preserve the informational content of emotional experiences while reducing their emotional intensity. This emotional dampening may contribute to emotional regulation and mental health. Interestingly, not all memories are strengthened during sleep. The brain appears to selectively consolidate certain memories while allowing others to fade. Memories that are tagged as important, either because they were emotionally significant or because they were explicitly intended to be remembered, are more likely to be consolidated during sleep. This selective consolidation makes sense from an adaptive perspective. The brain cannot store every detail of every experience. By preferentially consolidating important information during sleep, the brain can optimize memory storage and maintain a manageable memory load. Recent research has also uncovered a process called active forgetting during sleep. This may seem contradictory given sleep's role in memory consolidation, but both strengthening important memories and weakening unimportant ones serve the overall goal of optimizing memory function. Some studies suggest that sleep helps to prune weak or irrelevant synaptic connections, a process that may help prevent the brain from becoming saturated with information. This synaptic downscaling during sleep may help maintain the brain's capacity to learn new things and may contribute to the overall homeostasis of neural networks. The consolidation of memories during sleep is influenced by hormones and neurotransmitters, whose levels fluctuate across the sleep cycle. Cortisol, the stress hormone, has complex effects on memory consolidation. Early in the night, when cortisol levels are naturally low, conditions are optimal for consolidating certain types of memories, particularly those dependent on the hippocampus. Later in the night, as cortisol levels begin to rise in preparation for waking, the hormonal environment changes. Growth hormone, which is released primarily during slow-wave sleep, may also support memory consolidation and synaptic plasticity. The changing neurochemical environment across the night means that different sleep stages and different times of night may be optimal for consolidating different types of information. The relationship between sleep and learning has important practical implications. Students who pull all-nighters before exams are doing themselves a disservice. The hours spent cramming might create a sense of familiarity with the material, but without subsequent sleep, much of that information will not be effectively consolidated into long-term memory. Regular, adequate sleep is one of the most effective things people can do to optimize learning and memory. For athletes, adequate sleep is crucial for consolidating motor skills and improving performance. For musicians, sleep helps to refine motor sequences and integrate new techniques into existing repertoires. For anyone learning anything, sleep is not a luxury, but a necessity. As we approach the midpoint of our first journey through the sleeping brain, consider how remarkable this nightly process truly is. Your brain, seemingly at rest, is engaged in housekeeping that cannot wait, in memory work that shapes who you will be tomorrow, in waste clearance that protects your future cognitive health. Every night, without conscious effort or awareness, your brain performs these essential functions so crucial that evolution has made sleep universal across the animal kingdom, despite its apparent costs. This is the paradox of sleep. We are most vulnerable when we need it most, yet we cannot survive without it. The sleeping brain is not passive, but purposeful, not dormant, but remarkably, quietly active, working through the night to maintain the miracle of consciousness. The phenomenon of dreaming has captivated humans throughout history. Long before scientists began studying sleep in laboratories, people wondered about the meaning and origin of dreams. Ancient civilizations believed dreams were messages from gods or glimpses into the future. Freud proposed that dreams revealed hidden desires and unconscious conflicts. Today, neuroscience offers a different perspective, viewing dreams as the subjective experience of brain activity during sleep, particularly during REM sleep. Yet, even with modern tools, dreams remain mysterious. We still cannot fully explain why we dream, or what functions dreams might serve. Dreams occur during both REM and non-REM sleep, though they differ in character depending on when they occur. REM dreams tend to be longer, more vivid, more bizarre, and more emotionally intense. They often have a narrative quality, with the dreamer seeming to move through a sequence of events. The visual imagery in REM dreams is typically rich and detailed. Impossible things happen regularly. You might fly, breathe underwater, or find yourself in places that blend together locations from different times in your life. People in your dreams may merge characteristics of different individuals. Time flows strangely. Years can pass in moments, or moments can stretch indefinitely. Yet while you are in the dream, you rarely question these impossibilities. You accept the dream world as reality. Non-REM dreams are different. They tend to be shorter, more thought-like, and more closely tied to recent waking experiences. Non-REM dreams often lack the hallucinatory vividness of REM dreams. They may involve more mundane activities and more plausible scenarios. The emotional content is typically less intense. Some researchers have suggested that non-REM dreams might be better characterized as sleep thinking rather than true dreaming. However, the distinction between REM and non-REM dreams is not absolute. There is considerable overlap, and some non-REM dreams, especially those occurring late in the night, can be quite vivid and dreamlike. The content of dreams reflects a complex interplay of recent experiences, long-term memories, emotions, and random neural activation. Studies of dream content have found that dreams typically incorporate elements from the previous day or two, a phenomenon called the day residue effect. However, these elements are often fragmented and recombined in novel ways. An event that was emotionally significant during the day is more likely to appear in dreams, though often in a transformed or symbolic form. Dreams also draw on memories from throughout your life, sometimes bringing up experiences you have not consciously thought about in years. Certain themes appear repeatedly across cultures and individuals. Dreams of being chased, falling, flying, appearing in public naked or inappropriately dressed, taking exams, losing teeth, and finding yourself unprepared for an important event are reported by people worldwide. The universality of these themes has led some researchers to propose that they may reflect common concerns or adaptive challenges that humans face. Others suggest that these common dream themes may simply reflect the constraints and quirks of how the dreaming brain generates experiences. The emotional tone of dreams is often negative. Studies that have catalogued dream content find that feelings of apprehension, sadness, and anger are more common than feelings of happiness or joy. This negative bias might seem puzzling, but some researchers have proposed that dreams may serve an emotional regulation function, allowing the brain to process and cope with negative emotions in a safe, offline context. During REM sleep, the emotional centers of the brain are highly active, while the prefrontal regions involved in emotion regulation are less active. This pattern might allow for the activation and expression of emotions without the normal inhibitory controls, potentially facilitating emotional processing. The bizarre nature of dreams has led to several theories about their generation. The activation synthesis hypothesis, proposed in the 1970s, suggested that dreams result from the brain's attempt to make sense of random neural activity during REM sleep. According to this theory, the brainstem generates random signals that activate various brain regions, and the cortex tries to synthesize these random activations into a coherent narrative. This would explain why dreams are often illogical and bizarre. They are the brain's best attempt to create meaning from meaningless noise. However, this theory has been criticized for being too dismissive of the potentially meaningful content of dreams, and for not accounting for the fact that dreams are not truly random, but show systematic patterns and themes. More recent theories propose that dreams may actually serve adaptive functions. The threat simulation theory suggests that dreams, especially those involving threatening scenarios, allow the brain to practice responding to dangers in a safe environment. By rehearsing threat responses during sleep, we might be better prepared to deal with real threats when awake. The social simulation theory extends this idea, suggesting that dreams allow us to simulate social interactions and practice social skills. Evidence for these theories comes from studies showing that threatening and social scenarios are indeed common in dreams, and that individuals who are facing challenging situations in their waking lives often have related dreams. Another influential theory is the continual activation theory, which proposes that dreaming is a side effect of memory consolidation processes during sleep. According to this view, as the brain replays and processes memories during sleep, these reactivated memory traces occasionally reach consciousness, creating the experience of dreaming. The fragmented and recombined nature of dreams reflects the way memories are being shuffled and reorganized during consolidation. This theory can account for the presence of day residue elements in dreams and the fact that sleep and dreaming facilitate memory and learning. The proto-consciousness theory offers yet another perspective, suggesting that REM sleep and dreaming represent a state in which the brain tests and maintains the neural circuits necessary for consciousness. During development, REM sleep is particularly abundant, perhaps because the developing brain needs to establish and refine these circuits. Dreams, from this perspective, are not meaningful messages, but rather the felt experience of the brain running maintenance on its consciousness-generating machinery. This theory helps explain why infants spend so much time in REM sleep, even though they likely do not have dreams in the adult sense. Despite decades of research, the question of whether dreams have meaning remains contentious. Some researchers argue that dreams are simply noise, the subjective experience of random or quasi-random neural activity during sleep. Others contend that dreams, while perhaps not carrying the deep symbolic meanings proposed by Freud, nonetheless reflect the brain's ongoing processing of experiences, concerns, and emotions. The truth may lie somewhere in between. Dreams may incorporate meaningful content related to the dreamer's life, while also being shaped by the constraints and peculiarities of how the sleeping brain generates experience. One of the most intriguing aspects of dreams is that we rarely realize we are dreaming while the dream is happening. This lack of insight or metacognition in dreams is puzzling, because during waking, we are constantly aware that we are awake and can distinguish imagination from perception. The reduced activity in the prefrontal cortex during REM sleep may explain this lack of metacognitive awareness. The prefrontal cortex is crucial for self-reflection, reality monitoring, and executive control. When this region is less active, we lose the ability to critically evaluate our experiences, which is why the impossible events of dreams seem perfectly normal while we are experiencing them. However, some people occasionally experience lucid dreams, dreams in which they become aware that they are dreaming while the dream is still happening. Lucid dreamers can sometimes exert control over the dream, choosing where to go or what to do. Research on lucid dreaming has provided unique insights into the neurobiology of dreams. During lucid dreaming, there is a partial reactivation of prefrontal cortical areas, particularly in regions associated with self-awareness and metacognition. This suggests that the lack of awareness in normal dreams is indeed related to the deactivation of these prefrontal regions. Some individuals can learn to induce lucid dreams more reliably through training, and this has led to the development of various techniques and devices aimed at facilitating lucid dreaming. The study of dreams faces unique challenges. Dreams are inherently subjective experiences that can only be accessed through self-report. When someone describes a dream, we can never know if their description accurately captures what they experienced, or how much the act of recalling and narrating the dream has changed it. Dreams are also notoriously difficult to remember. Most dreams are forgotten within minutes of waking, unless deliberate effort is made to recall them. This rapid forgetting may be adaptive, preventing dream memories from being confused with real memories, but it makes systematic study challenging. Despite these challenges, researchers have developed methods to study dreams more objectively. By waking people during different sleep stages and collecting dream reports, researchers can examine how dreams vary across the night and across sleep stages. Advanced brain imaging techniques allow researchers to observe which brain regions are active during dreaming. Some researchers have even attempted to decode dream content from brain activity patterns, with limited but intriguing success. In one remarkable study, researchers trained a computer algorithm to recognize patterns of brain activity associated with viewing different types of images while subjects were awake. They then recorded brain activity while subjects slept. When the subjects were awakened and asked about their dreams, the algorithm could predict with better than chance accuracy whether certain categories of objects, like vehicles or buildings, had appeared in the dreams based solely on the brain activity patterns recorded just before waking. The relationship between dreams and REM sleep, while strong, is not absolute. Dreams can occur during non-REM sleep, and not all REM periods produce recalled dreams. Moreover, some neurological patients who have lost the ability to have REM sleep report still having dreams. This has led some researchers to propose that dreaming and REM sleep, while often occurring together, are actually controlled by different brain mechanisms. Dreaming may depend more on forebrain structures, particularly dopaminergic pathways, while REM sleep is controlled by cholinergic brainstem mechanisms. This dissociation between REM and dreaming complicates the question of why we have REM sleep, suggesting that dreaming might be a consequence of REM sleep rather than its purpose. The purpose of dreaming, if indeed dreams have a purpose, remains one of the great unsolved questions in neuroscience. It is possible that dreams serve multiple functions, or that different types of dreams serve different functions. It is also possible that dreams are simply an epiphenomenon, a byproduct of other sleep processes without any function of their own. What we can say with certainty is that dreaming is a universal human experience, one that has fascinated people throughout history and across cultures. Our modern scientific understanding, while incomplete, has revealed that dreams emerge from the complex interplay of memory systems, emotional circuits, and the unique neurophysiology of sleep. They are neither random noise nor profound prophecies, but something in between, a window into the remarkable, creative, and sometimes bizarre workings of the sleeping brain. Our journey through the first realm of sleep and dreams has taken us from the architecture of sleep stages to the mechanisms of memory consolidation, from the newly discovered glymphatic system to the enduring mystery of why we dream. We have seen that the sleeping brain is far from dormant. It is engaged in essential maintenance, consolidating memories, clearing waste, regulating emotions, and perhaps rehearsing responses to challenges. We have learned that sleep is not a luxury, but a biological necessity, shaped by millions of years of evolution and supported by intricate neural machinery. As you rest tonight, Your brain will cycle through its stages, each one contributing something essential to your health and well-being. You need not do anything but allow this ancient process to unfold, trusting in the wisdom of the body, the complexity of the brain, and the restorative power of sleep. The consequences of losing sleep extend far beyond simple tiredness. When you do not get enough sleep, your entire cognitive and emotional landscape shifts in ways that can be both subtle and profound. Sleep deprivation affects your brain at multiple levels, from the functioning of individual neurons to the coordination of large-scale networks. Understanding these effects helps illuminate why sleep is not optional, but essential, why your brain cannot simply push through without rest, and why chronic sleep loss carries such serious consequences for health and well-being. When you stay awake longer than you should, adenosine continues to accumulate in your brain. This molecular signal of sleep need builds higher and higher, creating increasingly strong pressure to sleep. Your circadian system may be telling you it is time to be alert, but the overwhelming homeostatic pressure begins to override these signals. The result is a state of conflict within your brain, where different systems are pulling in different directions. This conflict manifests as the foggy, disconnected feeling, familiar to anyone who has experienced serious sleep deprivation. The effects of sleep deprivation on attention are among the most well-documented and dramatic. After even a single night without sleep, your ability to maintain focus degrades significantly. Simple vigilance tasks, which require you to monitor a display and respond to occasional signals, become remarkably difficult. Your reaction times slow down, sometimes by several hundred milliseconds. More troubling, you begin to experience lapses, brief moments where you simply fail to respond at all. These lapses can last from a fraction of a second to several seconds, during which time you are essentially not processing information from the environment. During these attention lapses, something striking happens in your brain. Researchers using functional magnetic resonance imaging have observed that when sleep-deprived people experience these lapses, a wave of cerebrospinal fluid suddenly flows out of the brain. This is the same glymphatic clearance process that normally occurs during deep sleep. Your sleep-deprived brain, desperate for the waste-clearing function it has been denied, begins to initiate these clearance pulses during waking hours. But the price is steep. During these moments when fluid flows out, your attention completely fails. You zone out, missing crucial information, unable to respond to stimuli. When the fluid flows back in, your attention returns. This discovery reveals a fundamental trade-off. Your brain needs to clear waste, and if you do not give it dedicated sleep time to do so, it will steal moments during wakefulness, leaving you with dangerous gaps in consciousness. The prefrontal cortex, that part of your brain responsible for executive functions, planning, decision-making, and self-control, is particularly vulnerable to sleep deprivation. Brain imaging studies consistently show that after sleep deprivation, the prefrontal cortex becomes less active. This reduced activity corresponds to impairments in a range of higher-level cognitive functions. You become less able to think flexibly, to adapt your strategies when circumstances change, have more difficulty inhibiting inappropriate responses. Your judgment becomes impaired. You take more risks without adequately considering the consequences. Interestingly, not all prefrontal functions are equally affected. Simple, well-practiced tasks may show little impairment even after significant sleep loss. But tasks requiring innovation, creativity, or dealing with novel situations suffer dramatically. This pattern suggests that sleep deprivation particularly affects the most sophisticated and recently evolved aspects of human cognition. When you are sleep deprived, you can still follow routine procedures, but you lose your mental flexibility, your ability to see new solutions, your capacity to think outside established patterns. Memory formation and consolidation are profoundly disrupted by sleep deprivation. If you try to learn new information while sleep-deprived, you will encode it poorly. The hippocampus and associated regions show reduced activity during encoding after sleep loss, meaning the initial memory traces are weaker and more vulnerable to forgetting. Even if you manage to encode information while sleep-deprived, the lack of subsequent sleep prevents proper consolidation. Those memories remain fragile, and many will be lost. Studies have shown that people who are sleep-deprived are not only worse at remembering actual events, but are also more prone to forming false memories, confidently remembering things that never happened. The emotional consequences of sleep deprivation can be equally striking. The amygdala, a key structure for processing emotions, becomes more reactive after sleep loss. At the same time, the connection between the amygdala and the prefrontal cortex weakens. This means emotional responses become stronger and less regulated. You may find yourself more irritable, more easily frustrated, more likely to overreact to minor annoyances. Positive emotions are blunted, while negative emotions are amplified. The world takes on a darker cast. Small setbacks feel like disasters. This emotional dysregulation can affect relationships, work performance, and overall quality of life. Sleep deprivation also affects your ability to read and respond to social and emotional cues in others. Studies have found that sleep-deprived people are worse at recognizing facial expressions, particularly subtle ones. They have more difficulty interpreting tone of voice and body language. This can lead to social misunderstandings and conflicts. You might misinterpret a neutral comment as criticism, or fail to notice when someone needs support. These social cognitive impairments add another layer of difficulty to navigating daily life while sleep-deprived. The cumulative effects of chronic partial sleep restriction can be particularly insidious. Many people do not get one night of total sleep deprivation, but instead accumulate a sleep debt through many nights of inadequate sleep. Getting 6 hours per night instead of the needed 7 to 9 might not feel dramatically different on any single day. But over weeks and months, the effects accumulate. Studies comparing the effects of total sleep deprivation with chronic partial sleep restriction have found that 2 weeks of sleeping 6 hours per night produces cognitive impairment equivalent to 2 full nights without sleep. Yet people in the chronic sleep restriction condition often do not realize how impaired they are. They adapt to feeling tired, accepting it as their new normal, even as their performance continues to decline. This lack of insight into one's own impairment is one of the most dangerous aspects of sleep deprivation. After staying awake all night, you know you are impaired. But after weeks of getting too little sleep, you may feel you are functioning normally, even when objective measures show significant deficits. This disconnect between subjective experience and objective performance means that many people are walking through life significantly cognitively impaired without realizing it. They attribute their difficulties to other causes, never recognizing that they simply need more sleep. The health consequences of chronic sleep deprivation extend well beyond cognitive function. Insufficient sleep is associated with increased risk of obesity, diabetes, cardiovascular disease, weakened immune function, and even certain cancers. Some of these associations may be explained by shared underlying factors, but there is growing evidence that sleep loss itself directly contributes to disease risk. For example, even a few nights of restricted sleep can alter glucose metabolism and insulin sensitivity, creating a pre-diabetic state in otherwise healthy individuals. Sleep deprivation affects the hormones that regulate hunger and satiety, leading to increased appetite and preference for high-calorie foods. The immune system is particularly sensitive to sleep. During sleep, the body produces cytokines and other molecules that fight infection and inflammation. Sleep deprivation reduces the production of these protective substances and can impair the response to vaccines. People who are chronically sleep deprived get sick more often and take longer to recover from illness. The relationship between sleep and immune function may help explain why sleep needs increase when we are fighting an infection. The immune response itself can promote sleep, and this additional sleep helps the body fight off the invaders. Perhaps most concerning is the accumulating evidence linking chronic sleep deprivation to neurodegenerative disease, particularly Alzheimer's disease. As discussed earlier, the glymphatic system clears amyloid beta and tau proteins from the brain during sleep. When sleep is insufficient, these proteins accumulate. Even a single night of sleep deprivation has been shown to increase amyloid beta levels in the human brain. Over years and decades, chronic sleep deprivation could contribute to the buildup of these pathological brains. Proteins, potentially increasing the risk of developing Alzheimer's disease later in life. While more research is needed to establish causality definitively, the connection between sleep and neurodegeneration is compelling and suggests that protecting your sleep throughout life may help protect your brain in old age. Individual differences in vulnerability to sleep deprivation have been documented, though the mechanisms are not fully understood. Some people show marked cognitive impairment after even modest sleep restriction, while others remain relatively resilient. Part of this variation appears to be genetic. Researchers have identified genes that influence how severely someone is affected by sleep loss. These genetic differences affect everything from how quickly adenosine accumulates during wakefulness to how efficiently the brain can compensate for lack of sleep. There is also evidence that age matters, with adolescents being particularly vulnerable to the cognitive effects of sleep loss, perhaps because their brains are still developing. As we age, our sleep patterns naturally change in ways that can affect cognitive function and health. Older adults typically experience several shifts in their sleep architecture and circadian rhythms. The total amount of time spent asleep tends to decrease, though whether this reflects a reduced need for sleep or simply a reduced ability to sleep remains debated. More significantly, the quality of sleep changes. The amount of time spent in deep, slow-wave sleep declines substantially with age. Since slow-wave sleep is particularly important for memory consolidation and glymphatic clearance, this reduction may contribute to age-related cognitive changes. The amplitude of circadian rhythms also decreases with aging. The daily variation in hormones like melatonin and cortisol becomes less pronounced. Body temperature rhythms flatten. The suprachiasmatic nucleus, the brain's master circadian pacemaker, shows age-related changes, including loss of neurons and reduced expression of key neurotransmitters like vasopressin and vasoactive intestinal peptide. These neurochemical changes may weaken the clock's ability to generate strong, coherent rhythms and to effectively communicate time-of-day information to other brain regions. Perhaps most noticeably, circadian rhythms tend to shift earlier with age. This is called a phase advance. Older adults often find themselves becoming sleepy earlier in the evening and waking earlier in the morning. They may struggle to stay awake for evening social activities and find themselves wide awake at dawn. This shift in timing can create a mismatch between the older person's preferred sleep schedule and social or family expectations. The biological drive to sleep comes earlier, but the person may try to stay awake to maintain social connections or accommodate their partner's schedule, leading to chronic sleep restriction. These age-related changes in circadian rhythms also make older adults more vulnerable to jet lag and shift work. After crossing time zones or changing sleep schedules, older adults take longer to adjust and experience more severe symptoms during the adjustment period. Their circadian systems are less flexible, less able to shift in response to new time cues. This reduced adaptability reflects both changes in the central clock, in the suprachiasmatic nucleus, and changes in how light information reaches the clock. As the lens of the eye thickens and yellows with age, it filters out more of the blue light that is most effective for shifting circadian rhythms, making the clock less responsive to light exposure. The consequences of disrupted sleep in older adults are significant. Poor sleep quality is associated with cognitive decline, increased risk of falls, higher rates of depression, and generally poorer quality of life. There is a complex, bidirectional relationship between sleep and neurodegenerative diseases like Alzheimer's and Parkinson's. These diseases disrupt sleep through damage to brain regions involved in sleep regulation. At the same time, the resulting sleep disruption may accelerate disease progression by impairing glymphatic clearance of pathological proteins and by other mechanisms. Some researchers have proposed that sleep disruption might be both an early symptom and a contributing cause of neurodegeneration, creating a vicious cycle. Fortunately, many age-related sleep problems can be addressed. Maintaining good sleep hygiene becomes increasingly important as we age. This includes keeping regular sleep and wake times, getting adequate exposure to bright light during the day, especially in the morning, avoiding long or late afternoon naps, and creating a comfortable, quiet, dark sleep environment. Exercise has been shown to improve sleep quality in older adults, though vigorous exercise close to bedtime may be counterproductive. Managing other health conditions and reviewing medications with a doctor can also help, as many common medications and medical conditions can interfere with sleep. Sleep disorders are more common in older adults and should be identified and treated. Sleep apnea, where breathing repeatedly stops during sleep, affects a substantial proportion of older adults and can severely fragment sleep and reduce oxygen levels. Restless leg syndrome and periodic limb movements can prevent the onset of sleep or cause repeated awakenings. Insomnia, whether primary or secondary to other conditions, is highly prevalent and treatable. REM sleep behavior disorder, whether normal paralysis during REM sleep fails and people act out their dreams, is relatively rare but can be dangerous and may signal an increased risk of developing Parkinson's disease or a related condition. The recognition that sleep is essential for health has led to increased interest in interventions to improve sleep. Cognitive behavioral therapy for insomnia has strong evidence of effectiveness and is now recommended as first-line treatment. This approach addresses the thoughts, behaviors, and environmental factors that perpetuate insomnia without relying on medications. For circadian rhythm disorders, timed exposure to bright light can help shift the body clock to a more desirable phase. Melatonin supplements, when taken at the appropriate time, can also help adjust circadian timing, though the effects are modest. Sleep medications are widely used, but come with caveats. Benzodiazepines and related drugs can help people fall asleep, but may alter sleep architecture, suppressing deep sleep and increasing light sleep. They can also cause morning grogginess and carry risks of dependence and falls, particularly in older adults. Newer medications that target specific sleep-promoting systems in the brain may have fewer side effects, but long-term safety data are still accumulating. The general principle is that medications should be used judiciously and preferably for short periods, while also addressing underlying behavioral and environmental factors that affect sleep. Recent years have seen growing interest in optimizing sleep through technology and lifestyle modifications. Sleep trackers that monitor movement and sometimes heart rate or breathing can provide useful information about sleep patterns, though their accuracy varies. Some people find that tracking their sleep helps them identify factors that improve or worsen their sleep quality. However, there is also a risk of becoming overly focused on sleep metrics, leading to anxiety about sleep that itself worsens sleep, a phenomenon called orthosomnia. Understanding your individual sleep needs is important. While guidelines suggest that adults need 7 to 9 hours of sleep per night, there is individual variation. Some people function well on the lower end of this range, while others need more. Your own sleep need can be assessed by how you feel during the day. If you regularly feel sleepy during waking hours, struggle to focus, rely heavily on caffeine, or find yourself sleeping much longer on weekends than weekdays, you may not be getting enough sleep. True morning alertness and sustained daytime energy without excessive stimulant use are signs of adequate sleep. The concept of sleep quality is as important as sleep quantity. You might spend 8 hours in bed, but still not feel rested if your sleep is fragmented by frequent awakenings, or if you spend too little time in deep or REM sleep. Sleep quality is influenced by many factors, including room temperature, noise, light exposure, anxiety, pain, medications, and underlying sleep disorders. Creating conditions that promote continuous, high-quality sleep enhances the restorative functions of sleep. Chronotype, your natural tendency toward morningness or eveningness, is partially genetically determined and changes across the lifespan. Children are typically early risers. During adolescence, there is a dramatic shift toward eveningness, with teenagers naturally wanting to stay up late and sleep in. This shift is driven by changes in circadian biology and is universal across cultures. Unfortunately, it conflicts with early school start times, forcing many teenagers to wake up when their biological clocks are still promoting sleep. This creates a form of chronic sleep deprivation that can affect mood, academic performance, and even risk-taking behavior. In adulthood, chronotype gradually shifts back toward morningness, with the shift accelerating in later life. Respecting your chronotype to the extent that work and family obligations allow can improve sleep quality and daytime functioning. Extreme chronotypes, whether very early or very late, are associated with greater risk of various health and psychiatric conditions, possibly because of the chronic mismatch between internal biological timing and social schedules. The term social jet lag has been coined to describe the condition many people experience when their work-week schedule forces them to sleep and wake at times misaligned with their natural preferences. Then, they try to shift back on weekends. This weekly disruption of circadian rhythms may have metabolic and health consequences similar to actual jet lag. The field of sleep medicine has grown dramatically in recent decades, driven by recognition of sleep's importance for health. Sleep clinics can now diagnose and treat a wide range of sleep disorders using sophisticated techniques. Polysomnography, an overnight study that records brain waves, eye movements, muscle activity, heart rate, breathing, and oxygen levels, remains the gold standard for diagnosing many sleep disorders. Home sleep apnea tests offer a more convenient, though less comprehensive, alternative for evaluating suspected sleep apnea. Actigraphy, which uses a wrist-worn device to track movement patterns over days or weeks, can help assess circadian rhythm disorders and insomnia. The future of sleep research holds many promising directions. Advanced neuroimaging techniques are revealing the neural mechanisms underlying different sleep stages and how they relate to memory consolidation and other functions. Genetic studies are identifying the genes that regulate sleep need, circadian timing, and vulnerability to sleep disorders. This may lead to more personalized approaches to optimizing sleep. Researchers are exploring whether it might be possible to enhance specific aspects of sleep through targeted interventions. For example, playing specific sounds during slow-wave sleep can enhance the slow oscillations and improve memory consolidation. Transcranial electrical stimulation can also modulate sleep brainwaves. While these techniques are still experimental, they point toward a future where we might be able to make sleep more efficient or tailor it to specific needs. Understanding sleep at the molecular and cellular level continues to advance. Researchers have identified specific neurons and neural circuits that promote wakefulness or sleep. Optogenetic techniques, which allow researchers to activate or silence specific neurons using light, have revealed much about how these circuits interact. We now know that sleep and wake are not simply controlled by a single switch, but by multiple redundant systems that can partially compensate for each other. This redundancy ensures that sleep, being so essential, is robustly protected. Even when some components of the sleep system fail, others can often maintain basic sleep-wake cycling, though sleep quality may suffer. The question of why we sleep, while still not completely answered, has become clearer. Sleep appears to serve multiple essential functions. It allows the brain to clear metabolic waste through the glymphatic system. It enables memory consolidation, both strengthening important memories and weakening or eliminating unimportant ones. It supports synaptic homeostasis, preventing the brain from becoming saturated with strong connections. It facilitates emotional regulation, helping to process and integrate emotional experiences. It supports immune function and metabolic health. It may facilitate creative insight and problem solving. Rather than having a single purpose, sleep likely serves many functions that have accumulated over evolution. The universality of sleep across the animal kingdom suggests that these functions, or at least some of them, are not unique to humans, but reflect fundamental requirements of nervous systems. Even simple animals with rudimentary nervous systems show sleep-like states. The fruit fly, a favorite organism for genetic studies, sleeps in a way that shares key features with mammalian sleep, including homeostatic regulation and changes in brain activity. Genetic studies in flies have identified many genes involved in sleep regulation, many of which have counterparts in mammals, revealing the deep evolutionary conservation of sleep mechanisms. As our understanding of sleep has deepened, so has appreciation for its role in mental health. Virtually every psychiatric disorder is associated with sleep disturbances. Depression often involves early morning awakening and reduced REM latency. Anxiety disorders frequently involve difficulty falling asleep and restless sleep. Bipolar disorder is marked by dramatic changes in sleep need across mood states. Schizophrenia is associated with abnormalities in sleep architecture and circadian rhythms. The relationship is bidirectional. Mental illness disrupts sleep, and disrupted sleep can trigger or worsen mental health symptoms. Treating sleep problems can sometimes improve psychiatric symptoms, and conversely, treating the psychiatric condition often improves sleep. Sleep's role in development is profound. Infants spend the majority of their time asleep, with newborns sleeping 16 to 18 hours per day. Much of this sleep is REM sleep, which may be important for brain development. As children grow, total sleep time gradually decreases, but it remains much higher than in adults until adolescence. Sleep deprivation in children can manifest differently than in adults, sometimes causing hyperactivity rather than the sleepiness seen in adults. Adequate sleep during childhood is crucial for healthy physical growth, as growth hormone is released primarily during deep sleep, and for cognitive development, including learning, memory, and emotional regulation. The modern environment presents challenges for healthy sleep. Electric lighting allows us to extend our active hours well past sunset, which can delay our circadian rhythms and reduce sleep time. Screens from computers, tablets, and phones emit blue light that suppresses melatonin production, making it harder to fall asleep. The stimulating content on these devices can also interfere with the mental quiet needed to transition to sleep. Many jobs demand irregular schedules or require being on call, disrupting regular sleep patterns. Modern life's stresses and pressures can generate anxiety and rumination that prevent sleep onset or cause nighttime awakenings. Traffic noise, light pollution, and other aspects of urban environments can interfere with sleep quality. Creating a sleep-friendly lifestyle in this modern context requires conscious effort. Prioritizing sleep means treating it as important as diet and exercise, not as something to sacrifice when time is short. It means setting consistent sleep and wake times, even on weekends, allowing enough time in bed for adequate sleep, and creating a bedtime routine that signals the body it is time to wind down. It means managing light exposure, seeking bright light in the morning and dimming lights in the evening, minimizing screen time before bed. It means making the bedroom a sleep sanctuary, cool, dark, and quiet, used primarily for sleep rather than work or entertainment. The relationship between sleep and consciousness raises profound philosophical and scientific questions. What is the neural difference between the conscious experience of waking and the very different conscious experience of dreaming? What does the existence of dreamless sleep tell us about the requirements for consciousness? How do we explain the fact that during sleep, the brain can generate an entire subjective world, complete with sensory experiences, emotions, and a sense of self, all without any input from the external environment? These questions touch on fundamental mysteries about the nature of mind and its relationship to brain. Current theories of consciousness are beginning to incorporate what we know about sleep and dreaming. Integrated information theory proposes that consciousness arises from the brain's ability to integrate information across many specialized regions. During waking, the brain shows high integration, with widespread communication between different areas. During deep non-REM sleep, this integration is reduced, with brain regions becoming more isolated. May explain the reduced consciousness of this state. During REM sleep, integration increases again, potentially explaining the return of rich, conscious experience in the form of dreams. Though this integration is different from waking, perhaps explaining the different quality of dream consciousness. The study of sleep and dreams connects to broader questions about memory, learning, creativity, and the nature of thought itself. When we dream, our minds generate novel combinations of images, ideas, and emotions. This creative recombination might be a side effect of memory consolidation processes, or it might serve its own function, allowing the brain to explore possible scenarios and make unexpected connections. Some of the most creative moments of human history have been attributed to dreams, or the drowsy state between sleep and waking. Times when the mind is free from the constraints of logical, focused thought and can wander in new directions. As science continues to illuminate the mechanisms and functions of sleep, practical applications emerge. Optimizing sleep for athletes can improve performance, reduce injury risk, and speed recovery. For students, strategic napping and well-timed sleep can enhance learning and retention. For shift workers, bright light exposure and judicious use of naps and caffeine can help maintain alertness and minimize the health impacts of circadian disruption. For anyone recovering from illness or injury, ensuring adequate sleep supports healing. For older adults, protecting sleep quality can help maintain cognitive function and independence. The future will likely bring new tools and techniques for understanding and optimizing sleep. Artificial intelligence may help predict individual sleep needs and identify subtle patterns in sleep data that correlate with health outcomes. Wearable devices will continue to improve in accuracy and capability. New medications that target specific aspects of sleep regulation with fewer side effects may be developed. We may learn to enhance specific sleep processes to improve particular outcomes, strengthening slow-wave sleep to boost memory consolidation, or enhancing REM sleep to facilitate emotional processing. Yet, even as technology advances, the fundamental prescription for good sleep remains simple. Prioritize it, protect it, and respect its importance. Your brain needs sleep to function, to maintain itself, to prepare for tomorrow. Every hour of sleep you lose is a debt that must eventually be repaid. Every night of poor sleep weakens your cognitive abilities, dulls your emotions, and stresses your body. Conversely, every night of good sleep strengthens memory, enhances creativity, supports immune function, and improves mood. The journey through the science of sleep and dreams reveals a remarkable truth. Your sleeping brain is not merely resting, but actively working to maintain your health, consolidate your memories, and regulate your emotions. Dreams, those strange and sometimes vivid experiences that fill your nights, may serve purposes we are only beginning to understand. The glymphatic system, discovered so recently, shows us that sleep literally cleanses the brain. Memory consolidation during sleep transforms experiences into knowledge and skills. The circadian system coordinates countless processes across your body, all orchestrated by the simple cycles of light and darkness. This knowledge carries both wonder and responsibility. Wonder at the complexity and elegance of the systems that govern sleep. Wonder at the brain's ability to create entire worlds in dreams. Wonder at the precise coordination of molecular, cellular, and systems-level processes that unfold each night. But also responsibility to protect your sleep, to give your brain the rest it requires, to align your life, as much as possible, with the natural rhythms that evolution has built into your biology. As you prepare for sleep tonight, remember that you are engaging in one of the most important activities for your health and well-being. The transition from waking to sleep, the cycling through stages, the memory consolidation, the waste clearance, the dreaming, all of these will happen without your conscious effort. You need only create the conditions that allow them to unfold. A quiet room, a comfortable bed, a mind gradually letting go of the day's concerns, a body relaxing into stillness. Your brain has been working all day, processing information, making decisions, navigating challenges. Tonight, it will work in a different way, consolidating what you learned, clearing away what you do not need, preparing you for tomorrow. The glymphatic system will flow more freely, washing away metabolic waste. Neurons will replay experiences, strengthening synaptic connections that matter, weakening those that do not. If you dream, your mind will wander through landscapes of memory and imagination, recombining elements in ways that may offer new insights or simply reflect the brain's natural creativity. You have done enough for today. The work is finished. The decisions are made. The problems that remain will still be there tomorrow, and you will face them better with a rested brain. For now, there is nothing to do but rest. Let your breathing slow and deepen. Let your muscles soften and release their tension. Let your thoughts drift like clouds across a summer sky, appearing and dissolving. No need to hold on to any of them. The night is a gift, a time when consciousness fades and the deeper processes of brain and body can proceed uninterrupted. Every living thing needs rest. Every active system requires time for maintenance and repair. You are no exception. Sleep is not weakness but wisdom, not indulgence but necessity, not time wasted but time invested in health, clarity, and resilience. So, close your eyes now if they are not already closed. Feel the weight of your body sinking into the surface beneath you. Notice the gentle rhythm of your breath, the quiet darkness behind your eyelids, the gradual softening of awareness. You are safe. You are where you need to be. The only thing required of you now is to let go, to allow sleep to come in its own time, gently and naturally. Tomorrow will bring its own light, its own challenges and opportunities. But tonight belongs to rest, to the mysterious and essential processes that unfold in the sleeping brain, to the dreams that may come or may not, to the deep restoration that sleep provides. Trust in this ancient rhythm. Trust in your brain's ability to do what it has evolved to do. Trust in the quiet wisdom of letting go. Good night, and may your sleep be deep and restorative, your dreams gentle, and your awakening peaceful.